Now I'm going to show you how to work out the volume of a tetrahedron. So from here to here the length is A, from here to here the length is B, from here to here the length is C. So I hope you can see there's a solid there. Our job is to work out the volume of that solid. So I'm going to show you two ways of doing it. One is to use double integral. The other way is to use triple integral. So with double integral, your domain is on the xy plane. So this is your domain here on the xy plane. So this is your region, and you require the surface. So we've got our region here. So this is our region, and this thing here is our surface. That's the surface of the diagonal plane. This diagonal plane is the surface. So this is going to be our first way of doing it. Our second way of finding the volume is to use triple integral. So this thing here becomes a whole domain. So the whole solid is our domain, and then it spits out a value of 1. So this is a second way of doing this, and I've already explained why this works. So let's go back to the first way. We are now going to work out this one. After this, we will move on to this. But if we were to use this method, we need to know the surface. We need to know the equation of this plane. So revision time now. We now need to work out the volume of that plane. So our next task is to work out the equation for this plane. Once we've got the equation for the plane, then we can use double integral to work out the volume. So our first step is to work out the equation for the plane. So the equation for the plane is, so we're going to use vectors to come up with the equation of the plane. So so this point here is A across 0, 0. So the coordinates here would be A, 0, 0. The coordinates here would be 0, B, 0. The coordinates at C is given by this. So we need two vectors. Well, this vector here is given by this, because at the moment you've got at the moment this point here is from the origin, and then you move to here. And if you look at the point C, you start at the origin and then you move to C. So imagine you are standing here. So to get from A to this point here, you would have to go back to the origin, which is minus vector A, and then add vectors, add this thing. Basically, from here to here, it is this thing take away this thing. So this would be 0 take away A, that would be negative A. 0 take away 0, that would be 0. C take away 0, that would be C. So so from here, so you're standing here, and if you want to move to here, then this would be your vector, and then B would be this take away this, which would be minus A, and then this take away this, which would be this, and then this take away this. So this vector B is given by this. And remember, from our section on vectors, if you take the cross product of the two vectors, it will give you a new vector, and this new vector here will always be orthogonal to the other two vectors. So you blindly compute the cross product of the two, and remember, I'm expecting you to know this cross product. We've done it before. So it's going to be ijk, and then you discard for the first I. So this would be your first component, and then for the j, looking at the j, you discard. So that would give you this, and then it's blah blah blah, and then your normal vector is given by this. So let me just start again here. We know two vectors. We are trying to work out the equation of this plane. So we know two vectors. We start out with two vectors, blindly compute the cross product of the two. That will then give you the new vector, the normal vector. And then this normal vector will always be orthogonal to the other two vectors. It will always be at 90 degrees to the other two vectors. So now we've got the normal vector, which is given by this. So our normal vector is given by this. So remember, also from our section on vectors, the angle that exists in between two vectors is given by this thing here. So if two vectors are at 90 degrees to each other, then the dot product will always equal 0. And we've done this before, so I'm expecting you to know this. If something's at 90 degrees, then the dot product will always be equal to 0. So to describe your plane, you demand that the general vector. So let's create a general vector. We select a point anywhere. So point x, y, z. What is the vector that takes us? Remember, we are standing here. What is the vector that takes us from where we're standing to our general point? So what is this vector here to our point? Well, the vector there would be well, don't forget, this point here is from the origin to here, and then this point here is from the origin to here. So if you want to travel from here to our general point, you would need to move back a. So it's going to be minus vector a and then plus this general point. So this vector here is given by this. Hang on, is given by x minus a and then y and then z. So this is the vector that would take us from here to our general point. So to describe the plane, we demand that our general vector here to be at 90 degrees to the normal vector. And we've done this before. To describe a plane, you need to demand that the normal vector, when you take the dot product of the normal vector and our general vector here, this general vector here, you need to make the demand that the dot product of the two vectors to be equal to 0. So you need to make this demand here. So this is our normal vector because of this here. This is our normal vector. This is our normal vector, and this is our part of our normal vector. To describe the plane, you need to demand that the dot product of the two must equal 0. Because if you select any point on this plane, let's say this vector, if this vector is on the plane, then it would be at 90 degrees. If this vector here is at is on the plane, if this vector is on the plane, then it will be at 90 degrees to the normal vector. If you're not on the plane, let's say you're up here, then the vector here is not 90 degrees. So by you making this demand, you're really demanding everything where it's at 90 degrees to the normal, which is everything on the plane. Well, we've done this before, and I'm expecting you to know this by now. So to describe our plane, we need to make this demand. So now let's compute the dot product. So it will be this times this, that will then give you this, and then this times this, that will then give you this, this times this, that will then give you this. And you need to demand that everything adds up to 0. So now multiply this out, that will then give you this, and then from here multiply everything by, divide everything by a, b, c. That will then give you this thing here, and then tidy this up, and the equation of our surface is this, and you should have already seen this by now. That's where it came from. By using vectors, we can come up with the equation for that surface and rearrange it to make z the subject. The reason why we're making z the subject is because z represents our surface. Z represents our surface. Z represents this. So now we've got our surface. This is our surface. So now we can use double integral on our surface to work out the volume of this thing here, which I will explain in the next video. Okay.